Hello. Our project was video-to-video synthesis with semantically segmented video. The general motivation for this concept is to eventually be able to create realistic video without specifying scene geometry, materials, lighting, and dynamics for future graphic rendering engines. Our research problem was how can we generate photorealistic video given a semantically segmented video as input that appropriately depicts the annotated labels from the input. We are using the Cityscapes dataset for semantic urban scene understanding for our input and training. Our goal is to create a model that is capable of translating semantically segmented video into realistic video. Previous studies that provide background are general adversarial networks, which is where a generator is producing realistic synthetic data and attempting to trick the discriminator. Another study is image-to-image translation, which introduces pix-to-pix as a way to synthesize colored images from semantic masks or crude line drawings. And lastly, video-to-video synthesis, which is the video counterpart part of image translation.
Okay, going over our methods in experimental design, we use a simple conditional GAN or a CGAN to generate images from semantically segmented images. The GAN generators typically only take as input a random vector and latent space. However, the conditional GAN generator takes as input a random latent vector Z and the label or semantically segmented map C. And the discriminator also takes as input the additional condition as well. We use an implementation of the CGAN architecture that's introduced in the pix-to-pix architecture. The generator uses a UNet architecture that is an encoder-decoder architecture with skip connections, and the generator progressively downsamples until reaching the bottleneck and reverses the process. The low-level information is shared between the input and output through skip connections, since things like edges are shared between the input and output. And skip connections aren't actually weighted in this instance, as they just pass information from the source layer to be concatenated with the target layer. The discriminator is designed to model high-frequency details by restricting the attention to the local structure of image patches, and so this patch GAN only penalizes the structure at the scale of the patches and classifies each 70 by 70 pixel patch as real or fake. The discriminator is ran convolutionally across the image, and the responses are averaged to calculate the final output of the discriminator. Going over our results, the model is trained and tested on 256 pixel images from the Cityscapes dataset, and it was trained for 10 epochs, evaluated using a sequence of semantic masks as input. The generated video sequences are subject to flickering as the model does not have information from previous frames, so temporal coherence is not preserved. Generated images also lack some fine details. In this image, you see two random samples. On the left column is the original image. The center shows the semantic labels which were provided as input into the generator, and on the right is the output of the generator. And it appears to capture low frequency details. However, some high frequency details are absent. So in summary, our model is able to generate low frequency detail images given semantically labeled images of various street scenes. The current model leaves room for improvement as it currently fails to replicate some high frequency details that exist in the original source images. Our current model struggles with maintaining temporal coherence between generated image frames. The video results in flickering as the model does not have information about previous frames. However, the overall setting of the scene appears mostly consistent. We believe that our model can be improved with an appropriate dataset consisting of sequential image and semantic mask pairs. For future directions, we would also possibly like to generate masks utilizing game engine software that could generate video sequences using both original textures and replacing the textures with solid colors that represent specific semantic labels.